You're listening to Weird and Dead, the paleontology podcast that tells evolution's most embarrassing and bizarre stories. I'm Amy Atwater.
And I'm Meaghan Wetherell, and we're two living scientists who are weirdly excited about dead things.
On this week's episode, we're talking about dinosaurs in the Arctic, dinosaurs in the Antarctic, and how and why they lived in these far, far reaches of our globe.
Also, we talk about rafting again, but this time for rocks. Like always, our podcast talks about some disgusting stuff, so please read through the content warnings before continuing.
Alrighty then, we are talking about very cold and not necessarily cold, but very far north, very far south things today on our weird planet. This made me have a lot more appreciation for planet Earth and how cool it is. I will be getting latitude wrong this entire time. Oh
yes, I am fully prepared to watch you just suffer through latitude and longitude. In your defense, very similar words, but like historically, I have noticed that is not. You've got a lot of strong suits, honey, but this one is not one of them. And I get it.
It's not. My brain likes to not make sense of that. So this time we're switching it up, and I'm going to be talking about all things South Pole today, which I was going to gloss over all of the human stuff because I was like, meh, whatever, until I realized that all of these expeditions had scientists with them and frequently had geologists with them. So there are some really interesting overlaps with paleontology and like European racing to get to the poles, all those countries. So we'll just dive in with that. Giving you the year it's 1911. His name is Robert Falcon Scott. He has gone on a couple Antarctic expeditions before, really pushing the boundaries of how far south he could go. He sometimes worked with Shackleton, who we talked about a little bit in reference to leopard seals before, and they started out as friends, and then they decided that they were enemies because Scott decided he wanted to go explore a part of Antarctica that Shackleton was like, no, it's mine. I claimed it. And it sounded like it was very petty and stupid. And it didn't really matter because Scott had a much different ending than Shackleton did. So he goes on this expedition from, like 1910 or something like that to get to the South Pole. No one has gotten there yet. He's like, I'm going to fucking do it. Shackleton just failed. Fuck you, Shackleton. I'm going to go for it. And they had all of these mishaps. Like they took ponies because Shackleton was like, ponies are great. And then the ponies were not great. They were not acclimated.
Yeah, hooves. Hooves on ice. That's exactly what I think about as being good. Yeah, let's get these tiny ass little hooves and put them on slick surfaces.
Yeah, exactly. And we also, we know for
leopard seal food.
It's like, why not just try to use a leopard seal? I don't know. But obviously, because of a lot of other places and cultures and traditions, we can know that dogs do this very well instead. And it turns out that a Norwegian was also going to the pole at the exact same time. And he was using a dog sled setup and team. And they were like, yeah, we're fucking dogs. We're huskies. We're made for this. And Scott's expedition was not doing so great. And when they made it to the pole, the Norwegian guy had already been there like a month or so before him. They lost the race to the pole. The Norwegian guy just like left a tent and flag and shit. So if you scroll to your first picture, it's the picture of the dejected Scott and crew having just lost the race to get to the South Pole, looking really bummed out.
Wow, they do look really like most of the time when you look at photos from like the 1900s, people look kind of bummed out, but these people just look exhausted, like they just realized how useless horses are. Poor things.
And like racing to the pole, but I get it, it's there. And so they were super dejected.
I got to this patch of snow a little bit too slow.
And I mean, they're all from England and stuff like that. I'm sorry, the Norwegians already have quite the advantage when it comes to polar expedition. So, you lost to some folks from Norway. Like, I'm not surprised by that at all. Yeah. So, Scott wrote in his journal, I had to save this because I thought it's not that funny, but it's kind of funny. The worst has happened. All the daydreams must go. Great God, this is an awful place.
teenage girl's diary.
Yeah, and I love how he's saying the worst has happened, but the worst has not happened yet.
No.
So then it's like February. They're like, fuck, okay, we have to make do of this experience some way, somehow. And they hike towards this moraine where they actually saw rock instead of just ice for the first time in like 14 weeks or something like that. So they all start rock hounding and picking up rocks, and they find these fossil plants.
Oh.
And they're like, these are fucking cool. So they literally create a bag, 35 pounds of fossil plants that they then dragged. And then
consolation prize.
But they didn't get there, and they died on the ice
shit.
together with this bag of fossils in their tent. That they were going to die no matter what. There was some miscommunication with some other teammates or whatever somewhere else who were supposed to meet them with the dog sled team. That did not happen. But it has been brought up many times. I read in many accounts of like his so-called folly of adding additional 16 kilograms of rocks to their burden as they were all dying. So, whoops. But the fossils were Glossopteris, which is a Permian, so Paleozoic age plant that had only ever been found in places like South America, parts of Africa, and I think India prior to this, maybe not even all of those places. And this was around the time of Wegener figuring out how continents were moving and shaking. And these fossil, the name means tongue fern, you're interested. Anyway, the tongue fern became a pivotal part of reconstructing how the continents have changed since the Paleozoic, and how the position of Antarctica has also changed so drastically that it was at once hospitable to lush, beautiful plants and tropical animals as well. But before all of this concept of the moving continents was pretty out there. And it was because of finding fossils like the Glossopteris that were found next to all of these dead guys that helped us understand how continents change.
Do you think that they felt like it was kind of teasing the horses to have fossil plants that the horses couldn't eat? Like,
the horses were dead by this point, Meaghan. The horses were long dead.
Yeah,
they were eaten.
That's fair.
The benefit of taking horses over dogs is there's more animal to eat.
That is true, but you can't feed horses dead penguins. Or maybe you can. I mean, horses will eat flesh.
In a tough sitch.
Yeah, well, also just sometimes because they can.
Right.
Herbivores.
No judgment. No judgment.
Well, that's wild. I'm sorry that Glossopteris helped curse these men to their deaths, but
one other thing.
Glossopteris
I
is
have
really important.
to note is that these were not the first fossil plants found in Antarctica. The first ones were also found by some different Norwegian guy.
Oh, man.
Sorry. These are like the third, but arguably the most significant in terms of identifying them to the same plant in different continents. So good job, Scott.
Are we just saying that to make these people feel better?
They're dead.
We're not going to get haunted by them. They died in Antarctica.
No, they're haunting all those Norwegians. Or Norwegians? God! Oh! Norwegians.
Maybe this is a good segue to talk about paleolatitude and paleolongitude, which are terms that we're going to use a lot today. Latitude and longitude, mostly for Amy's sake.
Yes.
Latitude is the horizontal lines, which actually tell you how far up towards the poles or down towards the equator you are.
That's counterintuitive. It's counterintuitive.
Longitude is, are you facing the sun? Are you away from the sun? Longitude is harder to kind of reckon with as far as fossils go. It's actually much harder to figure out the longitude of a continent than it is to actually figure out the paleolatitude. And I will say, and paleolatitude just means ancient latitude. So continents move quite a lot. They bump into one another. They also disappear and are created. But knowing where a patch of land was helps you understand a lot about the climate and geology stuff. So discovering the ancient latitude is kind of important. And I have to say that while I do feel like I understand latitude and longitude probably better than you at the very least.
Well,
I definitely
low bar.
Did not fully understand paleolatitude because I forgot that our planet is 3 dimensions. And I just assumed, you look at a map, the map is flat. And sometimes I forgot that the world was not flat, which is why
flat,
part of my
Meaghan.
discovery in advance.
Solid burn.
Anyways, so I learned how magnets work this week, which was pretty exciting. So latitude is divvying up the round planet, but you can also figure out where your paleolatitude is by magnetic particles, which I understood, but because I thought the world was flat in my head, because the only other ways I've used compasses is to look at the difference between magnetic north and geographic north. It's always been a little confusing to me how that could get you paleolatitude. So to back up for a second, when you have magnetic particles that are preserved in a rock, usually in lava, they will basically become magnetically oriented with our planet's magnetic poles. So you can use those to tell important information about which direction was the pole, because apparently that flippity floppities, and also it wobbles a little bit. So it gives you a lot of information. But it doesn't just give you like which direction is north, because the magnetic pole is three-dimensional. It's not just horizontal as if the world was flat. It's also up and down. So if you have a particle forming and preserving that magnetic particle and locking it in place, so no matter where you move it on the planet, it can't rotate in a different direction. If you do that at the pole, it has a declination, which would be difference between magnetic north, which is where our magnetic pole is, versus true geographic north. It also has an inclination, which is how far down is it? Which direction is it going down?
Right.
If you're on top of a pole, it's 90 degrees. If you're not, it's some other variant of degrees.
Okay. Yeah.
Yeah. That's how you can tell paleolatitude, basically. It tells you that it's pointing straight through the planet. You don't seem mind blown by this. So clearly you haven't thought about it before. That's what I'm going with. This blew my mind. Absolutely. I was like, oh my God, this is how it's worked the whole time. Magnets go up and down. My compass doesn't do that.
I think it's good that we're going to get jazzed on different parts of this, because I had some times earlier that I was bouncing off the walls and Kelly was like, what the hell? And I was like, Gah! So, I think it's good that I'm learning. This is good. I mean, this is perfect because a lot of my shit is based on paleomag stuff. So to be able to have this foundation, very useful. And explaining why, because there's a pretty large margin of error with reconstructing paleo stuff. And the part of this is what you're describing is it's three-dimensional. There's all these different components. Those are all going to have their own baggage in terms of error. So
and if it's pointing down, it's of course pointing directly at the magnetic pole. And because our Earth is on a slight tilt, the magnetic pole doesn't always match, I don't think ever matches to the actual geographic North Pole. And the geographic North Pole is the thing that actually really matters as far as climate goes, because that's the part that points at the sun or doesn't point at the sun. So there is quite a lot of wiggle room. I did find a really cool website that seems pretty new. It's called paleolatitude.com. It is spelled the American way, so there's no stupid extra A's in there, British people. But it has like a listing of paleolatitude information. Shh, they did it wrong. It's not paleo, it's paleo. And yeah, it's as long as you click on something that was a continent at the time, you can get paleolatitude information. So you can't click on the west coast of Oregon and figure out where it was. But you can click, because that was in the ocean. But anything that was a continent that we have information for, it will do some interpolation stuff and tell you where it probably was, which is very cool.
That's handy, because I was doing a lot of eyeballing and yelling at these different articles for being all over the place, of acting like some of these Jurassic, Antarctic dinosaurs. They're like, they're so cold. And I'm like, no, it was literally like fucking 90 degrees all the time during this time period. Like, they weren't fucking cold. So and some places, I mean, there's a lot of debate about the exact placement of the continents, like it's great to have these tools, but people still fight about where exactly they would have been located.
Yes. And yeah, there'll always be some tweaking. The other way you can do paleolatitude is you can just take the continents and put them on a little model, and you can wiggle them around because you maybe know where plumes were and where things were separating over time. So you can get like some model answers as well. But yeah, magnetic is probably one of the number one ways that people get paleolatitude information. And with the Arctic, at least since going back to like the time of the dinosaurs, which is about as early as I looked, our continents, like the North America, Asia, we've kind of just been bumping up and down a little bit near the Arctic. There's not actually a shit ton of change as far as land mass goes at the Arctic Circle. It's up 10 degrees, down 10 degrees, but it's not like there was no continental mass and now there's continental mass. Like slighter variations compared to the story of Antarctica, which as far as continental drift goes, I understand it is a little bit more exciting.
It is indeed. This was a good challenge because my own research is based in North America. Every single fossil I've ever dealt with and handled for the most part is North American and is part of one of these former supercontinents that is not what Antarctica was a part of. So this was good to jump into Gondwana, and that's essentially the southern giant early giant continent thing. Yeah. So Pangaea, they're all together. Woo, 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 Pangaea, they're all together. Then they break up. So what we now know as modern day Africa, South America, Australia, India, and Antarctica was this giant landmass called Gondwana. If you've seen a sticker that says Reunite Gondwana Land, this is a bit of a tongue-in-cheek joke about bringing back this supercontinent that does not exist anymore. So what does that mean for Antarctica? When we talk about Antarctica today, it is very cold. It is covered in ice. There are giant ice sheets, glaciers that cover the entire surface. It has not always been that way. In fact, the major ice sheets didn't really get going again until the Miocene. So, like 20 million years ago. Before that, especially in the Cretaceous, so the end of the age of dinosaurs, into the Paleogene, so the Paleocene, Eocene thermal maximum. This is when the Earth is very warm. And that is a lot of the conditions in which life formed in Antarctica. It wasn't the ice sheets that it has always been. It was when it was more hospitable, both because of global climate, but also because of paleolatitude. So we know that about 450 million years ago, the crust that now makes up Antarctica was on the equator, which is mind-boggling on its own to think about. Yeah. And then by about 200 million years ago, Antarctica, the crust there was now joining up with parts of South America, Africa, India, and Australia to make up this Gondwana that we've talked about. And it did slowly split apart to create Antarctica as a separate continent. But this wasn't until probably, I didn't actually get an exact number on that. But we're talking probably like around the KT boundary, around then, just based on, and maybe even a little bit later because of the mammal fossils that we find there. So during this time period where we have a lot of the dinosaurs, so there are dinosaurs in Antarctica from like this early Jurassic time period and then also a early late Cretaceous time period. And Antarctica was totally ice-free at these times. Like it was very, very hot. We know from foraminifera fossils, so teeny tiny itty bitty microscopic animals that live in the ocean, can give us a good idea of their bottom dwelling creatures. So what the sediments, and again, if we're talking about trying to interpret what these past latitudes and climates may have been like, you want to understand like ocean temperature, ocean placement. So you use all these itty bitty ocean fossils. And they found out that Antarctica was literally during the Cretaceous was thought to be about 30 degrees Celsius, which is like 86 degrees Fahrenheit at its southern area, which would have even been getting close to the Antarctic Circle at that time. So it's still pretty far south, but it's so warm globally that it's not actually so much affected by cold weather as it would be periods of darkness. And that's what the animals would have had to be more adapted for than just the cold, when we're talking about at least the dinosaurs that make up this area. And I mean, it goes into a lot of the reasons why even today it is really, really difficult for organisms to live in the Arctic, the polar regions, and also in deep time. my poor segue back to you. You did a beautiful job, and then
Thank you. I appreciate the prompt and the compliment. Yeah, so when we talk about ice, which we are going to still talk about, even though there were no ice caps, it is important to recognize that there is a big difference between what we currently recognize as ice, although our children might not, versus like winter freezing, right? So like during the time of the dinosaurs, ice existed. It wasn't like a non-existent concept, but it probably was very seasonal. You have winter freezing and then summer warming. And in a lot of places, you didn't have winter freezing because it was too goddamn hot in the winter. But at the poles, at least in the Arctic pole, you probably still did have winter freezing in some areas. And the way that we can tell that is not just by us like doing weird hand wavy temperature modeling things, although frankly, we can do that too. There is geologic evidence for glaciers, for ice caps, and for things like winter freezing on lakes that is not an actual ice cap. And it does kind of differ. So some of that geologic evidence includes things like this weird mineral that sounds like a Wizard of Oz reference. It's called a glendonite, and it's like a calcium carbonate, like limestoney thing that it forms in cold water. And during the Mesozoic, it pretty much only seems to have formed in like the Baltic region. So it tells you that water was getting cold, at least down at the bottom of the ocean in kind of the northern portion of the northern hemisphere. You also get things like tillites, which is a glacier rock deposit. So if you have big glaciers, they make like kind of distinct looking formations. And we are going to talk now about rafting again, except this time for rocks.
I'm even more excited.
Yeah. Oh, yeah. It's not just sleepy, tiny, almost dead monkeys. It's also rocks that raft. So rocks, rafting. Another name for this is also dropstone. A dropstone is a special glacial feature. Basically, when you have a big glacier kind of plowing its way down a valley, it will pick up and incorporate rocks into the ice. And then when it meets the sea and it breaks into icebergs, those rocks are like suspended particles until the iceberg melts. And so you get like these big chunks of weird glacier rocks that melt out of icebergs and they fall, and they're called dropstones, both because they're dropping, but they also make like visible depressions in the sediment. So they like drop and dent it.
Wow.
Essentially.
They had some force to it as it was dropping.
Yeah.
Wow.
Yeah. So dropstones that come from ice rafting, especially with glaciers either knocking over rocks or pulling them up, is very frequently pretty big rocks. And it's a little bit weird to look at because you both get that divot underneath the rock because it's slammed into the mud. But it's also a very big difference in particle sizes, because when you're talking about rocks, you get tiny, tiny, tiny little particles deposited when the water is slow. And big ones are usually deposited when the water is fast, because that's the only thing capable of moving big rocks. Mm-hmm. But with dropstones and other glacial features, you get this weird, like lots and lots of little tiny sediments, so like slow water with like this weird giant big rock in the middle of nowhere. But you can also get those through other methods. They're usually smaller. So the dropstones we're going to talk about now are usually things like pebbles. Okay. But can you think of some things that might potentially kick rocks into a lake or into the ocean?
That would bring rocks into a lake or an ocean besides, well, let's see, some really kinky dinosaur sex lakes, probably number one.
Is that because the dinosaurs are incorporating the rocks into their sex lives, or they're dying mid-coitus and their gastroliths are being deposited?
Both.
Yes. So both.
I think, yes. Things that can, okay, so you're saying that are just like isolated rocks, though, not like a rock fall, some sort of landslide, lahar. Landslides and lahars will, but they bring down lots of them. Right.
So with these deposits, it's often like single ones. So one of the ways that you can get this is you can get this with trees or tree throw.
Tree throw.
Oh, yeah. Have you not heard this term before?
No. No.
It's a geomorphology thing. My husband is a geomorphologist, and so he talks about fucking tree throw all the time. So I've heard of it a lot. But Trees love to snuggle rocks very aggressively with their roots.
Yes.
And so they will actually break up the rock. And if a tree gets knocked over in like the wind, it pulls the rocks up. And so it's called throwing because it does move them. However, it's not like a fucking catapult, right? Like it's not sending them 2 miles into the ocean. Yeah. So you do get some short scale movement from trees. You can, of course, also have animals knock things into other things, right? So like it's not like dinosaurs were out there skipping rocks or anything, but you can get occasional rocks.
Well, you don't know that.
No, that's true, I guess. Maybe that was like what the tail was for on sauropod dinosaurs. It was like really good flinging action.
It can just be a bonus. That doesn't have to be
adaptive. It's a spandrel.
Yes, always. Always.
Okay,
now tell me.
Then some of the other ones are things like shoreline freezing. So instead of having like a big glacier, if during the winter you have like the shoreline gets ice on it, it's the same process, right? The ice will grab some of the bigger rocks that are up on the shoreline. And then as the ice melts, sometimes it'll drift out. You'll get like mini icebergs essentially. And so you'll have pebbles and cobbles dropped. So this is what people think was happening in a place that I should have looked up the pronunciation of. God damn it. Here we go anyways. The Jingar Basin is a Triassic/Jurassic site in China. And it was a pretty large lake system. And some recent research has suggested that even though in the Jurassic/Triassic, carbon dioxide was like 2,000 parts per million, so fucking enormous, so warm. Right. But even at that time, they think that there was seasonal freezing of this lake because you see these little stones that they think were being frozen by shorelines. There was one other method. And I agree that it probably was shoreline freezing. They think that the paleolatitude of this site in China was probably like 70 to 75 degrees in latitude, so pretty far north. So it would make sense. But they very casually mentioned in this paper that they didn't think it was algae rafting. And then I went down a rabbit hole of algae rafting.
At least it's biotic again.
So algae rafting is something that we have seen in like glacial marine settings. So not super far north necessarily, not like polar north, but like areas where you do have glaciers. And it's not like my first vision was like, you know, that nasty, nasty, thick like algae that forms on the tops of lakes and stuff during the summer. Like you get like a blanket of it. I thought it was like someone kicked a pebble on it and then it like drifts out into the middle of the lake.
Magic carpet righted it out.
And the thing is that could happen, but algae doesn't melt. So if you had a big old nasty carpet of algae, it would basically go down with the ship. You would only have algae plus rock, not algae or rock.
Right.
So that sort of algae rafting would have like a big organic layer. So that wasn't what they were talking about. What they were talking about is an algae that is called bladderwrack or sea grapes. It's like a seaweed. And I'm giggling because the scientific name, this is definitely not how the genus is pronounced, but it's fucus.
Oh, good.
Fucus, the algae, is responsible for algae rafting.
Yeah, it is. I mean, was there any other option?
No. Yeah. So fucus is a seaweed and it has a holdfast. And then it's called bladderwrack or sea grapes because it has like these little like inflatable things that help keep it upright.
Yeah, it sounds disgusting.
Yeah, it looks pretty gross. But because it clings to the rock, just like with tree throw, if the algae plant gets dislodged, sometimes a little pebble will come with it.
Oh, God.
So you'll get...
Oh, my gosh.
But the thing is, and because it has the little bladders that help it float, it can actually float quite some distance.
So it's a little, it's a raft. It's an algal.
It's a little raft.
Water. Little net, little exploration.
Yeah, it's dragging it along like a little anchor.
How cute.
It's very cute. Yeah. Usually, however, you get that kind of blown up onto the shore. So that's not necessarily going to explain finding a lot of drop stones. Also, they made a really good point that you only ever find one pebble per plant because they only have one holdfast. So they really can only do so much damage. Which is why I do believe these scientists when they say that they think it was ice rafting, well, specifically shoreline freezing in this area in China during the Jurassic when you have 2,000 parts per million of CO2.
Hot.
Which is nuts.
So hot.
Yeah.
It's getting gross. That is, yeah, because I mean, they so often it's referred to as these like ice-free world. And your point is that it is free of ice caps and there could still be ice present especially at, again, these more polar places, especially if you aren't getting light for 30 to 60 days, which is what you can be dealing with when you get within that 30 negative, or you can get quite cold. Yeah, because you have, so I had to think about this for my own, I was like, so the equator's 0, and the pole's 90. Okay, all right. That was my start for trying to understand when a paper says it was at 60 degrees latitude or even further south. I'm like, yeah, but what does that mean? So we can go ahead and scroll. You're going to scroll past a picture of the fossil Glossopteris that I forgot to tell you to look at. It's quite beautiful.
Oh.
It's like actually lovely.
Is this the death Glossopteris?
I couldn't figure out where that one is. It's probably like lost in the British Museum or something. So no, this is not one of the death tongue ferns. This is just a very pretty example from Wikipedia.
It is very pretty.
So that's like this vibe again. So when and they have other accounts of finding like beech leaves and other fairly broad leaf plants. And if you go into some of the basics of paleobotany and reconstructing paleo environment, the bigger the leaf, usually the more tends to be a more tropical climate. Not always, but a lot of times the bigger that. And then you can scroll on down to see exactly where I'm talking about in terms of where Antarctica was back in the days of Gondwana.
What a route.
So you can see the equator is going there. I can't even imagine. I think a lot of these reconstructions are based on paleo mag, which is interesting too. And all I want to point out here is that East Antarctica is at the 30th degree line latitude. So it is 30 degrees south of the equator. Okay. So that is around where you're going to find places like Cape Town, South Africa today, and a big chunk of what is now Australia. So again, just in thinking about the climates of those places, yes, they can get cold. Yes, they can get snow, but most of the time they're still quite warm. And the definition of the polar circle is, I think, 2/3 south. So it's 66.33333 degrees to be considered in the Antarctic polar circle. So a lot of these dinosaurs, so in the early Jurassic, we know that, we don't know the exact paleo latitude, but we do know that it was somewhere between probably 30 and 60 degrees. And so 60, for frame of reference, is my husband is from Juneau, Alaska, which is from about 60 degree latitude, but north of the equator, because Alaska is in the northern hemisphere. So again, like, Juneau is one of the farthest south cities you can be in Alaska. So it's really rainy and it definitely gets very, very dark. I've been there over Christmas or New Year's. It isn't 100% dark though. The sun rises around 10 a.m. and sets again by like 2 p.m. So you get about 4 hours even in some of the darkest days. So to really get complete darkness for a good chunk of the time, you need to be like above 60 degrees or below, depending on how you look at the globe.
Well, it's above regardless, right? Because it's counting the same. Yeah. It does. Yes. I nod. So just talking about some of these animals, we had this early Jurassic group of dinosaurs. So Cryolophosaurus, which is like so close to Brachylophosaurus, but cryo is going to be the indicator that it's cold, right? It's like the cold crested lizard. I want to just clarify that it probably wasn't that cold that much, maybe a couple times, but it wasn't like this fucking current Antarctic dinosaur. Like so much of the stuff I was reading was like, it was so cold. And I was like, no, it's
wasn't, but it did probably experience like 30 to 60 days of complete darkness in a given winter. And that is something really interesting. I read this interesting paper that was like, okay, the dinosaurs had two options. They could either hoof it on out of there, right? Because you're still attached to like South America, Africa, Australia. Maybe you can get north. And then they had this whole argument. They're like, yeah, but one of the dinosaurs from Antarctica from the Cretaceous stuff is an ankylosaur. Antarctopelta, and they were like, it can't migrate. It's worthless at that. It has such stupid legs and such a stupid body. I just was really, really entertaining. So the whole paper is going, well, if they can't migrate, then they have to essentially hunker on down. But a lot of times it doesn't seem like they have a lot of good evidence for hibernation or anything like that. It's just that because it was warm enough, there was still plant growth and they could rely on their other senses to get through the month to 2 months of pure darkness. They were just fine. It doesn't look like they were hibernating or anything quite like that because, again, while it was south, it still was quite warm for both the early Jurassic and this Cretaceous stuff. I also just have to tell you that as I was doing this, there were so many fun little Easter eggs of animals that we're obsessed with that have a tie to Antarctica. And one of the first ones is in the same formation that Cryolophosaurus is discovered is also a sauropodomorph. Ooh. So there's the first one for me to go, oh, what is its name? Glacialosaurus, something like that. Sure, we'll go with that. And then we've got a cool ankylosaur that's more like, the early Jurassic stuff is like 185 million years old. People really love Cryolophosaurus because it was one of the biggest theropod meat-eating dinosaurs of all meat-eating dinosaurs across the world at this time, which is pretty cool that it was in Gondwana. And it had this stupid kind of comb crest on its like face that has been argued if it had any. Yeah, it's very, very, yes, bird ornamentation style. And a lot of folks think it's probably for species recognition because it looks like it would have been worthless for like interspecies combat. And, people want to make it all about like violence. A lot of folks are saying, no, it was probably just for.
Because that's how chickens use their combs.
For looking good.
Is bitch slapping each other with their heads, right? It's definitely always aggression, never attraction.
Never.
Yeah.
Never. But do they do that? I'm not familiar enough with chickens. It seems like they would
don't.
Do everything.
Chickens don't headbutt. Chickens have nasty ass claws. So they'll stab each other with their claws.
Oh.
Yeah. Or peck each other.
Ugh. Yeah, well, that's probably what Cryolophosaurus was doing too. I don't know. Everybody loses it for Crimea River. It was definitely like dealt with darkness, but I don't think it actually had to. They don't think that it was probably like burrowing. There's no indication that any of these dinosaurs here were good at burrowing, but they did compare. This was also about the North Pole, hadrosaur legs to the legs of caribou. And how they are similar adaptively in this comparative method to show that they were well built for long migrations depending on the season. But then they just kept going back to the stupid ankylosaur and being like, ankylosaur, why do you not follow the rules? Yeah, it was like they literally said it lacked fossorial adaptations and was likely incapable of finding sufficient shelter. So it must have been subsistence overwintering to be the most acceptable means of adapting to these dark, dark polar days. And they also really want to point out that these dinosaurs, they're like, no. They were able to handle colder climates because these assemblages from the Jurassic and Cretaceous stuff have dinosaurs but lack turtles and crocodiles. And therefore, they also made a point that this is why dinosaurs did not go extinct at the KT boundary because they can't handle the cold. That's obviously bullshit because Cryolophosaurus was like building igloos and having itself a grand old time. So I take all of that with a big grain of salt because I have seen many dinosaur paleo sites where they just ignore turtle and crocodile material as they're digging up dinosaurs and pay no mind to it. And I'm also like, I don't think anyone is claiming that the asteroid hit and then just cooling is what did it to the dinos. I think there were a lot
a lot of other factors.
A lot of negative factors. Yes. So yeah, that's kind of the take on some of the southern dinosaurs, is that they could handle some cold. They definitely handle darkness, and the ankylosaurs couldn't migrate away.
Ankylosaurs were just like fucking basset hounds that were just stuck where they were. Wow, that's really interesting because the papers I read for the Arctic had excruciatingly different interpretations.
Woohoo!
Not only do they not do things like say, oh, well, the cold must have killed the dinosaurs. There are papers out there that straight up claim the cold is what actually gave birth to dinosaurs.
Oh,
which is kind of exciting.
I did not see that coming.
No, I did not.
You even
either.
wrote it in here, and I didn't.
I know.
I didn't even pick up what you're putting down.
It's a pretty alien concept, but some of our evidence comes from places like the Jungar Basin, which is that it was at 70 to 75 degrees latitude, so it was higher than Juneau. It probably had some colder winter temperatures. It probably had some darkness. But in one paper, they noted that, Jungar Basin is like I think it's maybe the only high latitude Triassic/Jurassic site that we found so far. So like that's part of why it's so exciting. There's not actually a ton of evidence for dinosaurs there. They found a couple of footprints. But this paper also discussed evidence for kind of a differentiation at the end of the Triassic between where dinosaurs were and where other tetrapods were if you looked across the planet. So during the Triassic and the Jurassic, they pointed out that the continents were all smashed together to an extent that essentially an animal could theoretically walk from pole to pole, essentially. Not all the way necessarily, and that would be a very exhausting journey, but there was like a lot of room for these animals to live in. And they pointed this out explicitly because at that point, you do not find herbivorous dinosaurs close to the equator. You find them further away from the equator because they theoretically were getting outcompeted by animals that could deal with hotter temperatures a little bit better. Because being an herbivore, you have gut biomes, right? So like you're already bigger, which makes you warmer. If you have gut bacteria kind of digesting things for you, they will also produce heat. So that makes you warmer. And then they also point out that dinosaurs had feathers of some kind or another. And it looks more and more like maybe that was an ancestral characteristic.
What?
Because every one of the big branches of dinosaurs has some sort of feather somewhere in its family. And so do pterosaurs. And while pterosaurs are not dinosaurs, they are below dinosaurs on that evolutionary tree.
Yeah.
So it seems likely that feathers were something that they had in common. And feathers initially evolved for thermal regulation, for insulation. So these animals, these dinosaurs, probably were a little bit hotter. They were probably warm-blooded. They may have had like some down. And that made it so that they weren't very competitive with other animals in kind of the middle zones of our planet because it was too fucking hot. So at the time of the Jurassic/Triassic, when you have 2,000 parts per million of CO2, you have seasonal freezing up at higher latitudes, but you have dinosaurs that seem to be dealing with that pretty well. And we don't have, at that point, we have evidence that they were up there because we have footprints and stuff, but we don't have a lot of high latitude sites at that particular time period with dinosaurs, so we can't tell if they were there year round. But they theorized in some of these papers that essentially that gave herbivorous dinosaurs in particular a little bit of an advantage when a big disaster happened at the end of the Triassic, known as the Central Atlantic Magmatic Province. So this was a longer eruption. It happened for, I think, several million years. And while it did also pump more of that goddamn CO2 into the air and was partly responsible for the extremely high CO2 of the Triassic, it also sometimes would create volcanic winters because it would erupt particles like sulfur, which means that the Triassic would go from really fucking hot to really fucking cold. And it means that when it would get hotter, those hot adapted animals could just kind of move up and out. When it would get colder, they would start to lose, so these tetrapods, not the dinosaurs, they would lose basically like niche space. But the dinosaurs had already been adapted. They were born in the cold, the very limited cold of the Triassic, and they were ready to take over. Which is why we see this massive explosion of herbivorous dinosaurs in the Triassic. explosion in the Jurassic.
Wow.
But we do notice that this actually kind of continues with sauropods in particular. So the biggest of the big herbivorous dinosaurs, they actually seem to have preferred cooler climates, which doesn't mean that they were like, let's go like shoot down an ice cap. But like as far as the climate extremes go, they were a little bit more interested in cooler climates than they were in the superheated kind of equatorial regions. So the Arctic gave birth to dinosaurs. That is
wild. I mean, I was just like, yeah, those large-bodied animals want nothing to do with the equator. And then I was like, elephants, rhinos, oh, those, but they're still nowhere as big as the sauropods. Like not even close. So as someone who went through the last part of my pregnancy in the summer, I wanted to be as far north as humanly possible. Yes. It's way hotter this summer, and I am just like, thank you, science. I'm not pregnant. I would be so miserable.
It's a more recent thing. I think that the paper I was reading came out like in 2022 or something. So it definitely has some ways to go to be proven, and looking for early Triassic sites with higher latitude are definitely going to be kind of key. But we do know that at least in the Arctic by the Cretaceous, dinosaurs were fucking adapted for the Arctic. Like, we still don't 100% know how they were dealing with the darkness. It looks like some of them maybe had pretty good eyesight. But we do suspect that some of them were living there year round. They weren't just like the ankylosaurs that just got ditched. They seem to have been
hey guys,
like, voluntary. So there's a Arctic site in Alaska called the Prince Creek Formation.
Yes.
And it had, at the time, it was about 80 to 85 degrees latitude. So really, really far north. Very close to the North Pole.
That's very far.
And because of that,
very close.
Right? That's super far, right? Like 90 is north, so that's not far off. And as a result, they would have had up to 120 days of continuous winter darkness, which is a lot. And
that's a lot.
Of course, when you have 120 days of continuous winter darkness, you also have 120 days of light. So that's the thing about the Arctic, is you can't just be like, let me invest in great night vision, because then you're going to be blind during the summer. So you have to find some way of dealing, right? You have to be adaptive. And at the time, it had a mean annual temperature of 6 degrees Celsius, which is 43 degrees Fahrenheit, which sounds insanely
pleasant.
Cold. Yeah, until so I looked up. Okay, sounds insanely cold to me. And then I looked up what the mean annual temperature is for both where I live in Central Washington and where you live in Colorado. My mean annual temperature is 8 degrees Celsius or 47 degrees Fahrenheit. Fuck my life. Why did I move here? And then yours is 10 degrees Celsius or 50 degrees Fahrenheit. So
it's too hot.
And of course, yes, it's not like Amy is out here sweating when it gets to be 60 degrees Fahrenheit. It does get very hot both in Colorado and in Washington. And it gets very, very cold. We have many days here of negative temperatures. So it is important to recognize that these mean annual temperatures are an average of the entire year. Like, you don't have a 40-degree summer. You have, negative degree winters and positive degree summers. Right.
Yeah. And it's just all on the opposite time of year if you're on the South Pole, which is always
that is weird.
Fun
I don't like that.
Remember.
Yeah. The hemisphere season thing, that one does fuck with me. But we do know that in Prince Creek Formation, even though, it is a lower annual temperature, it's not probably as cold as it seems when you think about mean annual temperature, but there probably were freezing conditions in the winter. There was probably occasional snowfall. But we do know for a fact that dinosaurs were here year round. So you need some very serious evidence to know that dinosaurs weren't ditching at certain times of the year. And that is, of course, eggs or babies. Because if you have eggs or babies, neither of those things are great at moving, neither eggs nor babies. So they're not very good at migrating.
Right. Yeah. But
eggs in particular.
Don't birds that migrate have their babies? Where do they, they don't nest all along.
I guess
they
that's a
nest
good point.
in one
spot. They do.
I don't
they
know.
do nest in one spot, but they also have much faster growth. Right. So it would have taken a sauropod or a hadrosaur dinosaur much longer to achieve sufficient growth to get the fuck out of there by the beginning of the winter. So they think that because there's a bunch of dinosaurs found in the Prince Creek Formation.
Yes.
70% of the families have a baby of some kind. So we know that they were probably laying eggs there. We haven't found eggs, I guess, yet, but we found like perinatal, so very close to being born, very recently born. And they also find several other growth stages. So there's like kind of a full family tree effect that's occurring there. And given the growth rates of dinosaurs, they don't think that they were growing in sufficient speed to get out of there and come back for the next year.
Yeah, I feel that.
Yeah. So in the end, we basically just think that maybe dinosaurs were too slow to be migrating annually, but they definitely lived in the poles, at least for some time of the year.
Yeah, some had those sexy long legs like those modern caribou, and some had stupid legs like an ankylosaur. I'm just kidding. I love ankylosaurs. It is just really funny to picture them migrating. Like, come on. That's great.
I love to picture like alternative travel modes for them. Like maybe they were like bodyboarding down the coast or something, and that's the only way they got anywhere.
Yeah.
But ankylosaurs, not long-legged.
They were, if anything, it's the turtle. Turtle.
It is the turtle.
They're just hunkering down and floating downriver and downstream and hoping that they get to a place where they can keep eating.
Just rafting.
Just rafting, of course.
But yeah, they were there at some parts of the year at the very least. And that's the story of polar dinosaurs, at least as it stands. I'm sure there's more research to come.
Thank you for listening. If you liked the podcast, be sure to rate and review us on your listening platform of choice. We really appreciate it.
If you'd like to hear more and support the show, follow us on Patreon for some exclusive bits or on our various social media platforms. You can follow Amy on Instagram at Mary Anning's Revenge.
And Meaghan on Instagram and TikTok at GeoPedalFabric, or both of us at Weird and Dead on Instagram and TikTok. This podcast is part of the Geology Podcasting Network.
Produced by the traveling geologist, Chris Spencer.
Cover art provided by Chris Spencer and the hosts.
Our theme song is Unlock Me by Praz Canal. Editing services provided by the amazing Katie Bradley.
Hosted by and researched by us, Amy Atwater and Meaghan Weatherall. Thanks for listening. I had a student in one of my Geology 101 classes at like the very end of the class come up and take like a selfie with me. I think it was like a Snapchat, and just tell me that the earth was flat and then walk out. What a